We'll start with what we're given. The weight of each crate, 150 pounds. What they call mu s of 0.65. So that's between the boxes. And then a different coefficient of friction between the bottom box and the floor of 0.35. They don't tell us anything about what's inside the box or how the boxes are weighted. So without that information, I'm going to make the assumption the boxes are uniform. So I'll assume that the density of the box is uniform. It's not that it's bottom heavy or top heavy or left heavy or right heavy. Without that information, that's a fair assumption we're going to make, and that'll come into play when we draw the free body diagrams. So we will find the minimum force required for any sort of motion to occur. We always operate in this class under the assumption of equilibrium. So all we can really see is when are we just going to leave equilibrium. So the applied force P that would cause it to just be on the verge of motion. And we'll see it's not quite as easy as it was in the first, what we did on Wednesday. So we'll assume that we'll start with there's a crate, the top crate and the bottom crate, or the top box and bottom box. They're not rigidly attached, so we can separate them and draw each of their free body diagrams. So we're not even going to start by necessarily considering how are these going to move, because the equilibrium is going to be true no matter what type of motion is occurring. So I'm going to split these out and draw their individual free body diagrams. So there's the top crate. So what forces or moments are acting on the top crate?
Weight.
Right, the weight of the crate itself. Each crate has a weight of 150 pounds. As I run the assumption, I'm going to assume they're uniform. So that means that I'm going to assume it acts in the geometric center of the crate. So the weight force at 1.5 feet from either end. It would also be half of 4.5. That's not going to come into play in this problem, though. Yeah.
You have the force P 0.5 off from the bottom.
Right, so on this crate, relative to the bottom of this crate, 0.5 feet, and it's an unknown magnitude of P, but we know it's pointing to the right.
Yeah. And you have the force of friction pointing to the left at the very bottom of the box.
Right, so this box, we removed the box below it, but we have to model what those two surfaces were doing. So one thing is there's a friction force between the surfaces. So we know that it acts on this axis. It will act parallel to the surfaces. And we presume that if we push to the right, that the box will want to move to the right. So because the friction force always opposes impending motion, there'll be a friction force I'll call FR1 pointing to the left on that bottom surface.
Is there a normal force too?
Right, anytime there's a friction force, at least for Coulomb friction, there has to be a normal force. So the normal force is the force from the bottom box pushing up on the top box. So we know the surface at which it acts. We know that normal forces always act, as the name implies, normal to the surface. But what do we not know about that force? Yeah.
Where it's located.
Right, we don't know where it is. We know that it's somewhere on this axis, but we don't know where we can put this. Let me take a step back, actually. So in general, the normal force is some distributed force, or distributed load like this. We don't know what that distribution looks like, and we don't really care for this problem. Yeah?
Can we assume that it would be in the middle because they're uniformly, the weight in the boxes is uniformly distributed?
We only can make that assumption if we were not applying a force P. So we can't make that assumption. But what we can say is this distributed load has some equivalent load that we call the normal force, and it acts at some equivalent location, which would be the centroid of this distributed load. So I'm not going to model it as the distributed load. So some value N1, and I don't know where it is yet, but I'll be able to figure that out. So I put the equivalent point load at the equivalent location, neither of which I know at the moment. And I choose to measure this from the right corner, which I'll call Q1. And we'll see in the equations why I did this. I'm measuring it from the right-hand side because that's where I think this would tip. I could measure it from the left-hand side also. This is just going to be a little bit easier in my equations. So N1 at some location I don't know yet. Right, so those are all the forces acting on this. There are 4 unknowns here because I don't know the normal force yet or the distance of where it's located, the friction force and P. So 4 unknowns in the free body diagram. I'm going to go to my second free body diagram before getting to my equations step. But any questions on the first free body diagram?
What's the Q1?
Q1 is just this point. So I'm going to reference it later when I get to the equation step. So now I can look at the bottom crate. This will have the same dimensions. So it's an identical crate. It will have the same weight of 150 pounds acting at the center of the crate. So we'll start there. What else is going to act on this crate? From, right, so it's resting on the ground, which I did not include in my picture. So I have to model what the ground does to the box. So the same idea as I used up here, some normal force I'll call N2, located somewhere along that base of support, which I'll call D2, and I'll name this point Q2, which I'll use later. Right, so we can presume, and this is where now we want to start thinking about how could this move. So which direction would we at least initially think this box would move relative to the ground? Right, we would think if we're pushing to the right that this would also want to move to the right. Again, if we get a negative answer for a friction force, we can come back here and fix that. But it's better to have some inkling for these. I'll call that FR2. Yeah.
We also have the first frictional force on this one too, except acting in opposite direction.
Correct. So just like we saw in frames and machines, we separated those surfaces, so we exposed in the drawings this FR1. We have to have that equal and opposite force, FR1, in this picture. Yeah.
Normal force N1 on the top, distance D1 from the right side.
Right, so same idea, equal and opposite forces at that equal and opposite location. So N1 down in this picture, D1 also measured from this top section here. Yeah. This is the gravity acting on the box. It will indirectly be in this picture because the normal force feels the 150. The normal force is also in this picture. So we don't include the 150 directly, but we will see how it transfers through. So the 150 from only this crate would appear in the picture. So these are all of the forces. There's no couples acting on then the second crate. Questions on the second free body diagram? We have 2 free body diagrams. We are working in equilibrium. So before we get to any of the motion, the impending motion things, I can write my equilibrium equations, which must be true if we're in equilibrium, which is all we're looking at is something just on the verge of becoming not in equilibrium. Looking at my first picture, I have some forces in the x. I have the applied force P and FR1 to the left. Because I'm ultimately looking for the value for P to cause motion, as I go, I'm going to simplify these equations a little bit, but you could just have the sequence of equations and still be able to solve this. But it'll be a little bit easier as we go to do it. So rearranging equation 1, the force of friction for this to be in equilibrium must be equal to the applied force P. In the y, we have the weight of the crate, the normal force from the bottom crate, the bottom box on top. So in this case, the normal force is 150. It happens to be the weight, but you can't make that assumption up front. You let the equations tell you if the normal force is equal to the weight. In the previous example, we saw the normal force was not equal to the weight. Here it happens to be, but that's not an assumption that's shown through the equations. And if it's in equilibrium, it also must be true if we take the moment around a point. I'm going to choose Q1 in this example. Then it has to sum to 0. We'll have the moment due to the weight of the crate, 150 times 1.5, minus N1 times D1. We know N1 at this point is 150, minus 0.5 times P. I can rearrange equation 3, I can get D1 in terms of P. Rearranging this, I get 1.5 minus 0.003 P is equal to D1. I have 4 unknowns still and only 3 equations, so I can go to my second picture and write its equilibrium equations. So in picture 2, I have that force of friction Fr1 minus force of friction Fr2. And that's all that's happening in the x direction. Putting everything in terms of P, Fr2, which is equal to Fr1, must also be equal to P. In the y, I have negative N1 minus 150 plus N2. I already know N1 was 150, so N2 must be 300. So the 150 pounds from the top crate, again, is not explicitly in picture 2, but it is indirectly there because they're coupled together by that N1, the normal force between the top box and the bottom box. And I can take the sum of moments around Q2 in picture 2, in which case I'll get 150 times 1.5 minus N2 D2. I know the value here is 300, plus N1 D1 minus FR1 times 4.5. which I know is equal to P. Rearranging equation 6.1, I also know D1 in terms of P. So I can rearrange equation 6 and solve this for D2 in terms of P. And in this next solution step, you'll see why this is useful. So 1.5 minus 0.0167 times P. Those are all the equilibrium equations I can write, are 3 for the first free body diagram, 3 for the second. I've rearranged them over here. I've used 2 of them, or I numerically solved for N1, N2. I have 4 equations left, but there's still 5 things I don't know, FR1, FR2, D1, D2, and P. So it's not yet a solvable system of equations, but I'm out of equilibrium equations to write. Now I want to consider what are the possible motions of the system, one at a time. And that will give me at least one additional equation to make this a solvable system. So now looking at this, what are possible ways that motion could happen in the system? Move, how specifically do they move? Right, they could both be stuck together and slide relative to the floor is one way. Right, so the bottom box stays still, the top box tips over. Yeah.
They could both slide to the right but at different rates. So the top box could slide more than the bottom box.
It's a physical possibility, but in this case, because we're only looking at things on the verge of motion, that would not come into play. So in a dynamics problem, yes. In this we won't consider that. Right, the bottom box stays stationary, the top box slides relative to it. Yeah.
And they both tip together?
Right, they're stuck together and they tip at that bottom corner. They actually called it B, I called it Q2. So those are the 4 possible ways we could be on the verge of motion. Once it's in motion, these equations 1 through 6 are no longer true. So we can only analyze it up to when's the first time that something is going to just begin to move. So there's 4 different scenarios we came up with. So we're going to one at a time consider what happens when that scenario is true. So I'm going to call scenario A, in my notes, box 1 slips on box 2. One being the top, 2 being the bottom. So this will introduce a new equation or equations that describe this scenario happening. And these are all, again, on the verge of happening. So if box 1 is about to slip relative to box 2, mathematically, what must be the case? There's 2 frictional forces, so more specifically. Right, so FR1 must be, well, it's always equal. If we're in equilibrium, we already know it's equal to P. So that's true no matter what scenario is taking place. Yeah.
US times N1.
Right. If it's on the verge of slipping, that means that this friction force is at its maximum. And if we pushed a little bit more, this would not be able to counter how hard we're pushing. So for box 1 to slip top versus bottom, FR1 must be at its maximum value. So FR1 is at its max when it's equal to mu times S. Specifically, these surfaces mu, which was 0.65. So the second condition I considered is box 1 tipping, box 2 staying still. So box 1 tips at Q1. In scenario B, we ignore what we added in A, so I'm going to introduce a different equation 7. I'll call it 7B. Is 97.5 pounds. So that's the force it would take to max out the value of FR1, and then be on the verge of slipping relative to the bottom box. D1 would equal 0. So when 2 surfaces are in contact, when the normal force is all the way under the pivot point, that's where we say that it's about to tip over. So it's a little bit different than if it was a point in contact with the surface. Then we say tipping is when the normal force is 0. So when the centroid of that distributed load is all the way at that extreme, that's indicating it's about to tip over. So the new equation is D1 is 0. So again, that would mean N1 is all the way under that right corner. Now I have a different equation 7. I ignore 7A, but I use now 7B and those same equilibrium equations. And now what happens if I put 7B into 3.1, this gives me a different value for P. This gives me a value of P of 450 pounds. So we're going to tip box 1 at its corner. I would have to apply 450 pounds of force. Now we can start making some comparisons. Could this happen? Right. Unless we instantly are able to apply 450 pounds, which we're going to assume we can't, then we're going to kind of build up to how hard we're pushing. By the time we got to 450 pounds, we've already gone past 97.5. Once we get here, it's in motion, which means that equations 1 through 6 are not true anymore. So we could not achieve this. This can't happen. So we had to solve for it, but it's not a feasible scenario. Right, so scenario C, the order you do these in doesn't matter, but I chose box 2 slipping on the floor. So a different equation 7 for this one. Right, so it's now these 2 surfaces, so we're using their coefficient of friction, 0.35 or mu s prime, and their contact force, N2, which we know is 300 from equation 5.1. So if FR2 is equal to 0.35 times 300, and from 4.1 we know FR2 is equal to P, that means for condition C, that P to cause this is 105 pounds. We've already eliminated B. Again, compared to A, this can't happen because box 1 would already be sliding on box 2 by the time box 2 would be sliding relative to the floor. So scenario C is not the case either. So finally, the fourth way is we said box 2 tips at its corner, Q2. Right, so the normal force N2 is directly under this pivot point, making D2 equal to 0. We now combine equation 7D with 1.1 through 6.1. Specifically 6.1, if D2 is 0, that means that P sub D is 90 pounds. We've eliminated B, we've eliminated C. This is less than A. We're looking for the smallest force here because that means it's the hardest we can push. So now A can't happen because it would already be tipping at D by the time it would slide relative, the top would slide relative to the bottom. So the smallest value here, the minimum of this is the maximum that we could push before there would be any motion in the system. And we would say that the first thing that would happen is once we get to 90 pounds, the two boxes together would start to tip at that bottom corner, Q2, or in that picture, B.